Greetings to everyone watching. We are very pleased to show you all our designing process of the wastewater treatment plant and sewerage for La Fortuna. Starting off with the case description, La Fortuna is in the Huetar Norte region of Costa Rica, Alajuela province. It has an extension of 225 square kilometers with a population of around 15,000 inhabitants. Tourism is the most important economic activity, as it receives around 3,000 tourists per year, with higher activity between June and November. However, La Fortuna has several weaknesses in the water resource sanitation. The wastewater is mainly managed by septic tanks, with low capacity and operation and maintenance. For this reason, the design of a sewerage system and a centralized system for wastewater treatment are projected. Around 2004, La Fortuna joined forces to develop alternatives and studies, which was key for the development of the selection and design of the following treatment plant. The per capita demand was calculated using the domestic consumption data. The estimate of the total equivalent population was made by the total consumption in the sala and the demand, which was used for the estimation of the floating population. The population and growth rate for both resident and floating population were based on census information. The design period is 25 years and the wastewater production flow is 109 liters per second. The purpose of the treatment plant is to comply with the Costa Rican legislation, as you can tell by the effluent characteristics. For its accomplishments, a preliminary and secondary treatment are needed. For the sewerage, the design started from the review of the topographical information to set flow direction, wells location, and the effluent areas. The total water flow includes the wastewater flow, which was calculated for each effluent area, considering the land use and residential and mixed population. Also, the infiltration and upstream flow were considered in the total flow. The sewerage system network diameters, slopes, and full hydraulic capacity used were also calculated. The design sewerage system covers these 10 communities that are shown in the general view scheme, and it turned out to be a 28.2 kilometer sewerage network. Next, you can see here the top view of the design sewerage. These pie charts also show the sewerage characteristics. From this, we know that throughout the sewerage system, it is used the minimum diameter, minimum medium slope, and the use of hydraulic capacity shows that the pipes will not be working at a very high capacity. As an important remark, the design was based on the axis of sustainability, biological processes, reduction of energy consumption, and applicability in Latin America. When it comes to the pre-design of the technological options, it is important to clear out that the environmental processes and hydraulic and architectonical designs were considered in the project. However, soil study and both electrical and structural designs were not considered. Also, for the pre-selected options, the Costa Rican legislation was taken into consideration. The respective boundaries for each option were considered, and also the 15 meters of distance between the plant and the discharge river. As you can see here, option A is made up of an anaerobic pond followed by a trickling filter with a settler. Every technology has 2 units, and you can see the dimensions and the boundary on the right. Next, option B. This one's similar to option A, however, this one starts with an UASB. Every technology has 4 units, and as you can see, the dimensions and the boundary are on the right as well. Option C has an USB followed by an anaerobic filter. Option D is a lagoon system. However, due to the dimensions of the ponds, it was not possible to comply with the Costa Rican boundary legislation, so this option was removed in the pre-design. Last, option E is made up of a high-rate anaerobic pond, followed by a trickling filter and a settler. Each technology has 2 units. The dimensions and boundary are on the right.
Regarding the selection model, we used a multi-criterion one. The goal here is to propose a long-term solution to the sanitation problem in La Fortuna. This methodology is based on setting a series of criteria to analyze, including the economic, environmental, technical, and social factors. In order to evaluate these aspects, we first proceeded to study the indicators shown in the screen. As a remark, we defined the operation and maintenance cost for the social criterion, because that's what the population is going to pay on the associated tariff. We took all this data and submitted to the 4 technologies explained before into a mathematical model. It's important to address that in order to propose an efficient and accurate solution, we need to take into consideration the needs of the people that are going to use the technology. That's why we interviewed the president of the ASADA, And by the SATIS ponderation, we were able to define, for this case in particular, that the environmental criterion is the most important as it ranked with a weight of 44%, while the economical aspect added just a 4% to the decision taken. After applying the mathematical model, it became clear that the option D had the best results. The hydrate anaerobic pond and the trickling filter is the most suitable technology for La Fortuna case.
We visualize this plant in the future. First, in the blue circles, we have all the processing facilities involved in the wastewater treatment in order to achieve acceptable effluent characteristics prior to being dumped into the river. Second, in the yellow circles, we have all the sludge processing facilities for active sludge digestion and for stabilized biosolid recovery. Third, in the green circles, we have all the processing units involved in the biogas recovery and production of clean energy. And last, in the red circle, we have all the administrative facilities. As you can see, the high rate anaerobic pond participates in both wastewater and sludge processing. This is because we propose to direct the active sludge to this unit for its digestion, enhancing the energy recovered and minimizing the amount of residual biosolids, and without the need of another external unit, for example another sludge biodigester. The operational maintenance cost is critical to achieving sustainability in relation to a wastewater centralized treatment system in La Fortuna. Therefore, an optimization algorithm was applied to find the secondary treatment design variables that minimize the operational maintenance cost, which are the objective function. The objective function comprises the electricity and maintenance and repairs costs, which are mainly affected to the treatment design variables. Also, said objective function is subjected to some restrictions that are all the mathematical expressions and design criteria that describes the behavior of the process. The nonlinear multivariate constraint optimization problem was solved using MATLAB nonlinear programming algorithm. As a result, the secondary treatment proposed is effective and also minimizes the operational maintenance cost, taking into account the land availability and other design restrictions. Now, each component that makes up the system will be discussed next. Also, the dimensions of each component will be displayed on screen. First, in order to prevent a reduction of the overall treatment efficiency and to protect from damage the equipment used in subsequent stages, the quartz solids are retained in quartz screens and followed by fine screens. The grid is removed in a horizontal grid chamber. Taking maximal advantage of the warm climate in the region and the land availability, a high rate anaerobic pond is an effective, low-cost, and simple solution for the removal of biodegradable organic matter. This technology is more effective and compact than conventional anaerobic ponds, but maintains its constructional and operational simplicity. In this unit, the wastewater and the active sludge are introduced at the base of the mixed chamber. Also, in the high-rate anaerobic pond, the sludge digestion and the sludge settlement are separated. The biogas recovery from the mixed chamber is accomplished through a biogas collection structure, which is projected in medular form. The wastewater exiting the high-rate anaerobic pond is then furnished additional treatment in the high-rate trickling filter. The application of wastewater to the packing medium is done by a 4-arm rotating distributor. The use of plastic packing in comparison to rugs was preferred because the former has more void space, which enhances the air circulation through the media, which is particularly important according to the relatively high organic loads at that unit inlet. Also, the packing depth of 3 meters was selected because, or in order to reduce the amount of energy required for pumping the wastewater from the high-rate anaerobic pond to the top of the trickling filter. On the other hand, the use of natural ventilation may result in the formation of malodorous gases and a reduction of treatment efficiency in periods when the wastewater and air temperature are very close. For this reason, we recommend the use of low-pressure axial fans for each treatment unit. The use of the low-pressure axial fans may be distributed around the periphery of the treatment filter in order or to assure a uniform air distribution across this unit. Then, the wastewater that percolates through the trickling filter and the solids that are released from the packing medium are collected in a drainage system, which drives them to a secondary clarifier. In that secondary clarifier, solids are separated from treated wastewater. As you can see, the clarified effluent satisfies the BOD effluent characteristics according to the Costa Rican law, which maximum permissible level is 50 mg per liter. Also, the overall wastewater treatment system achieves a 95% BOD removal. All the sludge from this unit is sent to sludge processing facilities, detailed later on.
It's important to address that all the wastewater line was designed as a gravity working system, with the exception of the trickling filter, given the necessary aerobic conditions. Since this filter is located on an elevated position, it needs active pumping to function. At the end of this process, the effluent is dumped into the Danta River. However, it is vital to evaluate how is this going to affect the ecosystem. According to the Holland Quality Index, the Danta River places on the first category, being this one the best water quality. We have evaluated the effects of dumping wastewater into the river, and we have determined that the VOD and the river increases in such a way that the category is still the same. It's important to clarify that the anthropogenic dissolved oxygen and the ammonical nitrogen needs to be analyzed too in order to have a real conclusion. Moving on to the sludge treatment process, we have the sludge thickener. These units receive the sludge from the secondary settler and concentrate it. After that, a big part, the 99% of sludge, goes to the deep camera of the anaerobic pond to increase the organic load and be digested, and the rest goes to the drying beds. The supernatant is recirculated onto itself in order to enhance the process of the thickener and to avoid odors and septic conditions. The rest goes to the effluent of the trickling filter. It's important to mention that these units are elevated in order to avoid posterior pumping on the process. The sludge, after being digested on the deep camera of the high-rate anaerobic pond, is transported to the drying beds with a purge frequency of 7 days. This sludge takes around 21 days to be totally dried, and we use one bed every week. Thus, when the first one is totally dried, it can be filled with a new purge. We also want to mention that we designed 2 more beds than necessary in order to prevent possible operation difficulties. Moreover, the distribution of the beds on the space has been designed to simplify the access of the vehicles to the biosolids. These biosolids can be used as compost for the farming region around La Fortuna, so it even could represent an extra income. In addition, with this design, we are able to obtain biogas generated by the hydrate anaerobic pond. This biogas is conducted to the biofilter to refine it, and it is stored on the settler gasometer. After that, the gas goes to the microturbine to generate energy. If this gas is not used, we have provided a torch in the model which can be used to burn the methane and avoid greater contamination. The estimated methane flow, energy production, and microturbine workload are displayed in the chart. Moreover, the carbon dioxide reduction by 2045 is about 18 tons per year. In order to take advantage of this reduction, the plant can participate in the carbon markets to sell this carbon offset, either on foreign markets or using the UCC for the Costa Rican carbon offsets. Otherwise, it may keep this offset as own to start the effort to be a carbon neutral plant in the future. Lastly, it is crucial to take into consideration that the biogas production depends on the population growth. That's why we analyze this behavior through time. We estimated that in the 17th year of operation, the plant will need another gasometer to handle the methane flow. Moreover, before the 22nd year, it is necessary to have a storage routine for the gas in order to have the microturbine workload set at around 70%.
In order to meet La Fortuna's rapid increase in wastewater annual production, the implementation of 2 parallel units of a high-rate anaerobic pond and a high-rate trickling filter is proposed as a reliable and cost-effective solution. The simultaneous installation of both units is suggested to guarantee treatment if one unit fails or requires maintenance. However, in order to minimize operational maintenance costs, we recommend operation of one unit only until treatment capacity allows it. Therefore, 100 anaerobic pond is expected to treat effectively all the wastewater production until the year 2034, when the setup of the second unit is recommended in order to avoid overloading of the first unit. Similarly, one treatment filter is projected to have capacity to treat the complete effluent from the high-rate anaerobic pond until the year 2034, when the setup of the second unit is suggested for satisfactory operation. Finally, according with the gravity thickener design proposed, we recommend the setup of the first unit in 2023 for effective treatment filter sludge concentration, and the second unit in 2040 to concentrate the sludge coming from the secondary treatment filter.
Now for the hydraulics of the treatment plant, we designed two main pipelines. One for sludge, which is the one you see in red, and one for water, which is the one you see in blue. Also, for the optimization of the whole system, we use as many pumps as possible, taking into perspective that we can use gravity as an advantage for us to move the fluids. In total, we have 7 pumps distributed, as you can see, with the corresponding power. We consider a few things for the selection of the pumps. Number 1, the shortest distances to place the pipes and so to create the less losses of the hydraulic load. Number 2, a low velocity of the fluid. Number 3, pipes with a diameter enough for it to carry the velocity. And number 4, different times of operation of the pump that gives us the best flow rate and thus velocity and diameter. In terms of electrical consumption of the whole plant, we model how the electric load and demand vary within the years, depending which pumps are working. And so we obtain the total power consumed per year plus illumination and the amount of energy that the plant will produce due to the gas, to check how much the plant will have to pay to the local energy company and to determine if the plant can be self-sufficient, and of course how much it will cost to the plant to operate. Regarding financial terms, some of the most significant aspects in the selection of wastewater treatment plants are the investment cost, since they relate the quality of the raw wastewater and the treatment level. The design of the wastewater treatment plant proposed has a total capital investment of $3,283,277 mainly attributed to equipment investment cost, which arises to $720,365, where the high-rate anaerobic reactors, trickling filters, and the microturbine represent 60% of the total investment cost. The main drivers for the cost of the sewerage system taken into account were excavation with backhoe and soil transportation needed for piping installation, which comprises cutting, removal, and transport of existing pavement, and the corresponding construction of the new asphalt layer. It's worth mentioning that for each section, the associated labor force was already considered. The total capital investment of the sewerage system is $1,902,862, mainly attributed to 160 and 400 mm pipes, wells, and excavation cost, which represents 70% of the total investment cost.
Low operation and maintenance costs are critical in order to achieve sustainability to the system proposed. The estimated operational maintenance cost includes personnel, electricity, sludge disposal, maintenance, and repairs, and electromechanical equipment reposition cost. As you can see, in the design period, the annual operational maintenance cost is mainly attributed to electromechanical equipment reposition cost, representing nearly 44% of the total cost. On the other hand, the cost of electricity is negligible. This is because the plant is self-sustainable from an energy standpoint. Other economic indicators are displayed on the screen. It is worth saying that the wastewater treatment plant design proposed is cost-effective solution in terms of operational and maintenance. The projected user fee is between 6 to 12 cents per month during the design period. The administrative facilities were inspired in national architecture and tropical essence. This includes classrooms, administration, lab facilities, reception, employee rooms, and bathrooms.